Hey guys, we're going over X-ray physics, week 6. So we're going to go over X-ray interactions to start off with. So there's 5 different types of X-ray interactions that we're going to cover. And the first 3 are pretty much the only ones that are important to us. You have coherent photoelectric effect or photoelectric absorption effect, Compton scatter, and then you have paired production and photo disintegration, which doesn't matter, and paired production doesn't really matter to us. We just have to know that photo disintegration blows up a nucleus. Pretty simple. Paired production, it converts pure energy to mass, and just know that at 1.2 million electron volts, you'll have paired production. So we'll knock those 2 out of the way right now, and we'll jump into coherent scatter. So you have coherent scatter is also known as Rayleigh scatter, Thomson, or classical scatter. And these occur at very low energies, which is from 0 to 10 keV, and they don't ionize. So pretty much they don't do anything, and they're not diagnostic for us whatsoever, but we just have to know about them. So anything that's produced in the range of 0 to 10 is going to be coherent or classical scatter. The second one is photoelectric effect or photoelectric absorption effect, and this occurs anywhere from the range of keV of 10 to 60. This is where X-rays are absorbed, and this is what gives us whiteness on the film. So that'll actually ionize the inner shell electrons, and these again are absorbed, but they're not actually scattered. So whereas coherent it scatters low energy keVs, and Compton scatter, which we'll get to, it scatters them as well. The photoelectric effect is actually where X-rays are absorbed. So we'll move on to Compton scatter, and key here is anywhere from range of 60 and up, which we can only get to 125, but 60 to 125 keV, we will have Compton scatter. And so our goal as X-ray techs is to lower the amount of fog which is created from scatter as best as possible. So Compton scatter is responsible for 95% of the fog that shows up on X-rays. And it's increased when you increase kVp, which is why we always have an optimal kVp for spine imaging of 70 to 90. Anywhere like outside of that range, as you get up further, you increase the kVp more, you're going to increase scatter. It's not related to the atomic number, and that's different than the photoelectric absorption effect, which is. So the higher density, or the higher the atomic number, the more electrons or X-rays that are actually going to be absorbed. But Compton scatter, it's going to happen in any sort of tissue, regardless of the atomic number or the density of that tissue. So that pretty much sums up the X-rays stuff. Pretty simple. And then we'll move over to like how do you control scatter. There's about 5 different things here, or 4 different things we use. One is using optimum kVp, so trying to keep the kVp as low as possible while getting us the desired results. Because when you increase kVp, you increase scatter. We can use compression. There's like compression bands. If you lie on a recumbent table, that'll increase or that'll decrease scatter because you use less MAS. So the more scatter is also attributed by the more MAS you have, because the more electrons or more X-rays that are actually ejected in a beam is going to create more scatter. There's a higher probability that those will diverge and they'll cause scatter. So if you can use compression, when you compress a tissue, there's less tissue space to go through, and you have these X-rays that'll penetrate, and it takes less MAS. So if you use compression, we have kVp, using optimum kVp, and collimation. You collimate certain areas out, you're going to have less scatter because there's less X-rays that are going out. The best way, the most effective means of controlling scatter is using a Bucky grid. And when we're talking about Bucky grids, there's a few things we need to talk about. You have a linear parallel grid, which is pretty much the crappy one. You have a focused linear grid, and you have crosshatch grids. And these grids are pretty much like the linear grid. It's going to be like you have your Bucky here, and you're going to have strips of lead in here, going long ways here, longitudinally. And what the goal is as you have a beam that diverges, you only want the perpendicular beams, the ones that are going directly into the film. The ones that start to diverge, you want to get rid of those. And that's what we consider to be scatter, and that creates fog. What happens is, in an ideal world, this will go and it'll hit these lead strips as it's off its target angle. And so we're considering this the crappy one because it's just compared to the better ones, it sucks, because we'll talk about the focused linear grid. The focused linear grid is similar to this concept. It's still running up and down, superior, inferior, but these aren't coming straight out. They're actually at an angle. So they're angled in towards the center, and as the beam diverges, it's going to hit that. So it's supposedly set up at the exact angle that your beam diverges. And these are more important because when you set up your focused linear grid, which is this guy right here, it's set to a specific source image distance. Because so if you were to change the source image distance, you're going to alter that because the beam is going to diverge differently. Anyway, so that's the most complicated part of it, really. Then you have crosshatch grids, which we don't like to use those because in chiropractic we like to be able to tilt the tube. So if you tilt the tube up, now you can't get an angle because these are going to be blocking your x-rays. So we don't use crosshatch grids in chiropractic. We can have moving grids, and moving grids, according to Everidge, they're expensive, more things can break. But you have a single stroke grid, which is the really ghetto kind. It's pretty much like you take a grid and you pull it back with a rubber band and you snap it forward as it shoots an x-ray. Pretty shitty. We have reciprocating grids, which oscillate, but they go back and forth really quickly. They're better, but then oscillating grids are the best, and those are the ones that actually kind of they go in all directions, so it makes a more clear image, so you don't actually have, and the purpose of these moving grids is so that you don't have grid lines showing up on your x-ray. And that's pretty much all I want to cover right now, so good luck studying.